So we have these thermal quantities. We have specific heat, latent heat of vaporization, and latent heat of fusion. And specific heat, we know, is defined as the amount of heat required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So this applies to temperature changes which occur only within a single fixed state or phase. Latent heat of vaporization is discussing heat being added when changing phase, specifically between the liquid and the gas states. Latent heat of fusion is the same, except that instead of changing between liquid and gas states, we're changing from either a solid to a liquid or a liquid to a solid. So the definition for latent heat of vaporization is the amount of heat required to vaporize 1 kilogram of a substance. And again here, latent heat of fusion has a definition of the amount of heat required to melt 1 kilogram of a substance, or to solidify, to freeze 1 kilogram of a substance. And there are these quantities. We've studied them, we've used them in problems, but there's this question, which is how could we actually calculate what one of these is equal to for like some new unknown substance that was just recently discovered? And the answer is we use the method of mixtures. So it's a slightly different method based on which one of these three we are calculating. And we're going to see an example where we calculate C, specific heat. Then we're going to see a second example where we calculate LV. We're not going to worry about LF. That's okay. So here's the example. Let's say we find some new metal, discover some new metal, and we want to know what its specific heat is. First thing you do, heat this metal with known mass, measure its mass, and its unknown C. Heat it to a known temperature. You could do this by heating up some water until it starts boiling, right? And once it's boiling, we know its temperature is 100 degrees. And then you place the metal into the boiling water for a few minutes so that they reach thermal equilibrium, such that the metal and the boiling water both have a T of 100 degrees. Once it's at 100 degrees, you place the heated metal into an insulated cup which contains cold water with known mass and known temperature. So before putting this metal into the cup with water, you have to measure the temperature of the water and the mass of the water. Once you put it in, once you place that heated metal into the cold water, you let the metal and the water reach thermal equilibrium. So let them sit for a little while. Then you measure the final temperature of the water and the metal. You do this by putting a thermometer into the water, and then once you get the reading, you know that that's also the final temperature of the metal, since they are in thermal equilibrium. So there's heat transfer going on here. And if all of the heat which leaves the metal is transferred into the water, then we could say the heat gained by the water, the magnitude of this, will equal the heat lost by the metal, will equal this. But of course this assumes that we have no heat being transferred from the metal to the external environment, like the cup. So that's kind of an assumption we have to make. Now we plug in MC delta T for each of these terms, Q water and also for Q metal. And over here we have MC delta T. Here you see MC delta T. We know the mass of the water because we measured it. The specific heat of water is a given, it's a known value. We know the mass of the metal because we measured that. We know the final temperature of the water and the metal is what we read off the thermometer, the final reading. We also used the thermometer to measure the initial temperature of the water. And then we also knew that the initial temperature of the metal was 100 degrees. That's what we selected. So if you follow this procedure, then we know every variable in this equation except for Cm. Thus we can solve for it. So here's another example of the method of mixtures where instead of finding C, the specific heat, we're going to find LV. And what I'm going to assume is I'm going to act like we don't know what LV equals for water. So I'm going to describe this process for water, but really you can use it for any liquid where we know its specific heat. So all you need is to be able to write down what the specific heat is of that liquid, and then you can find its LV. First step, heat up some water until you have steam. Then pass that steam, which we know to be at 100 degrees, pass it into cold water of known mass and known initial temperature. So you have an insulated cup with cold water. Before passing in the steam, you measure the mass and the initial temp of the water, the cold water, and then you pass in the steam. The steam will condense into water, right? And then it'll cool so it'll condense into 100 degree water. The 100 degree steam condenses into 100 degree water, and then the 100 degree water cools as it mixes with the cold water until thermal equilibrium is reached. Then you measure the final temperature of all the water together, the cold water, the initially cold water, and the initially hot water, the 100 degree water. And you also measure the final mass of the water together, all of it. Once you know the final mass of all the water, you can subtract from it the mass of the initially cold water in order to find the mass of the steam. So there's heat transfer again, and if all of the heat leaving the steam is transferred to the water, then the heat gained by the water will equal the heat lost by the steam. And as before, I put absolute values here so that we don't have to worry about negative signs. And of course, we assume that there's no heat being transferred to the insulated cup or any other external environment. So here's the tricky thing about this. The heat that is gained by the water, that heat only goes toward producing an increase in the temperature of the initially cold water. Right? On the other hand, the heat that is lost by the steam is lost in two phases, or two steps, let's say. In the first step, the steam condenses and it loses heat. And then there is some additional heat being lost. Right? So the steam condenses, it becomes 100 degree water. Then that 100 degree water lowers in temperature as it reaches thermal equilibrium with the initially cold water. So we have two different terms on the right side. You plug in MC delta T for this first Q water, because the initially cold water merely changes temperature. You plug in M times LV for the steam that is condensing. That's how we find the heat that is given off when that steam condenses. And you plug in MC delta T for the 100 degree water, which then cools to reach thermal equilibrium. So we know the initial mass, we know the mass of the initially cold water because we measured it. We know the specific heat of water, that's what we must know. And if we're not using water, if we're using some other liquid, then we must know its specific heat. We know the final temperature of the water because we measure it with a thermometer, and that's the same as this TF here. We know the initial temperature of the water because we measure it with the same thermometer. We know the mass of the steam. We got it by taking the total mass of all the water at the very end minus this mass. That's what this is. And same MS term here. Again, we know the specific heat of water, and we know here's our last variable. This is the only unknown so far, LV. We said that this is equal to this, and we know TI, the initial temperature of the water, the 100 degree water, is 100 degrees. The steam condenses as 100 degree water, and then that 100 degree water starts at that temperature and cools till it reaches the final temperature we measure. So we know every variable but LV, this. Okay? So you solve for LV, and that's how you calculate the latent heat of vaporization. Now there's a problem with both of these experiments. The problem is that heat will be lost to the surrounding environment, such as the insulated cup. It's inevitable. Heat will be lost. Here's how you can fix this. You fix it by carefully choosing the operating temperatures of the experiment. So for example, I'm going to show you what this means with reference to the first method of mixtures we saw, where we found C with the metal. So for example, if the room temperature is 20 degrees, then you design your experiment so that the metal's initial temperature is 30 and its final temperature is 10. Okay? This is a really clever trick. You design the operating, you carefully choose the operating temperatures, right? Design your experiment in this way. Because if you do that, then as the 30-degree metal, as it goes down to 10 degrees, in the first half of that cooling process, right, it'll be moving to 20 degrees, and it'll be giving off heat, some of which will be given off to the environment. Some will be lost to the environment, right, which hurts our experimental results. But then, as it makes the rest of its descent from 20 degrees down to its final 10 degrees, well, in that phase, in that portion of its temperature decrease, it'll be colder than the external environment, so it'll absorb some heat from the external environment. So what this does is, this way, heat isn't just lost to the surrounding environment, it's also gained from the surrounding environment. And this makes the total energy loss and gain much, much closer to 0 joules. So that's a clever trick. I explained it with reference to the first method of mixtures that we saw, but we could apply the same trick of choosing our operating temperatures to any method of mixtures. So you choose the final and initial temperature so that the middle is room temperature. So smack dab between the final and initial, you want room temperature. That's the trick. So I'm going to show you a second problem with the specific heat experiment, then I'm going to show you a second problem with the latent heat experiment. This first problem applies to all method of mixture experiments. Then we're going to look at some specific problems. So here's the second problem with the specific heat experiment. After boiling the metal, right, after boiling it in the hot water to get it up to the initial temperature of 100 degrees, there may be some hot water droplets on it. So if those hot water droplets, if they make their way into the cold water, the initially cold water in the cup, then there will be this extra increase in final temperature, which we haven't accounted for. So here's the second problem then with the latent heat experiment. Steam usually is passed, the 100-degree steam is transferred or passed into the cup through a tube. But some of that steam will condense early on in the tube, so the heat released when that steam condenses early, that heat released will not make it into the water like we assumed. Thus, this is not equal, right? Which one is bigger? Which one is bigger? Well, there's some extra heat being released by steam, which doesn't make its way into the water, which means that because of this early condensation, the heat that is gained by the water will be slightly less than the heat given off by the steam. Okay, so this is a problem. Now, the last thing we're going to look at is some quick notes on absolute zero, and those begin here. Here they are. Temperature. We know this. It's derived from the average molecular kinetic energy of molecules making up a body or substance. But this implies that there's the lowest possible temperature, right? Specifically, there must be some lowest possible temperature when the average molecular Ke is at its lowest, which is 0. And that would occur when the molecules have stopped moving. This temperature has a special name called absolute zero. And we've already seen that temperature is not something we can measure directly. Instead, it's something we must calculate. We must calculate from some other quantity. And we saw that the other quantity used by thermometers is the height of a column of alcohol. But really, temperature is best measured by measuring pressure. And the reason is because the zero pressure coincides with zero temperature. So they both are 0 at the same moment. They're both 0 when Ke is 0. Now get these notes down, I'm going to run out of time. Kelvin scale is a temperature scale based on pressure of a fixed mass of a gas with constant volume, which means that the Kelvin scale measures temperature relative to pressure.